This is Youngi Kim, MS course student in Artificial Intelligence and Mobility Lab. And this presentation is a summary of the paper, Adaptive Federated Learning in Resource-Constrained Edge Computing Systems, submitted to IEEE Journal on Selected Areas in Communications 2019. In this paper, three reasons are mentioned as to why the federated learning is emerging. First, the data generation rate will exceed the capacity of Internet. Also, it's inefficient to send all data to remote cloud, occupying huge bandwidth, and the raw data may have privacy information. And multiple edge nodes can work with the remote cloud in some cases. For these reasons, it's meaningful enough to study about how to utilize the limited resources at the edge for optimal learning performance. Based on precedent studies, the author focused on the gradient descent-based federated learning algorithms. This learning algorithm consists of two processes. First one is the local update. Each edge node performs gradient descent to adjust the model parameters to minimize the loss function defined on its own dataset. The other one is the global aggregation. The aggregator aggregates model parameters obtained at different edge nodes and sends an updated parameter back to the edge nodes. In practical environment, the relationship among the frequency of global aggregation, the training accuracy, and resource consumption is quite complex. These are main contributions of this paper. At first, analysis of the theoretical convergence bound of gradient descent-based federated learning incorporates non-independent and identically distributed data. Second, proposal of a control algorithm that learns the data distribution, system dynamics, and model characteristics to adapt in real time. Third, evaluation for the performance of the proposed algorithm using real datasets both on a hardware prototype and in a simulated environment. The thing is, there are two key features in this study. One concerns a dynamical determination for the global aggregation frequency during learning process, and the other takes account of non-IID data at edge nodes. This slide represents the loss function and the problem with a simple expression. Equation 1 is the local loss function, which is used for computing at each node I. It's trained by the local dataset D sub I. Equation 2 is the global loss function. It aggregates information from all of local loss functions. At bottom, the learning problem is to find the parameters that minimize the global loss function. The algorithm in this slide is a distributed gradient descent algorithm in a logical view. There are two inputs. Tau is the number of local update steps between two global aggregations, and T is an integer multiple of tau. When tau is equal to T, this algorithm is equivalent to the centralized gradient descent. In line 3, local updates performed in parallel at each node. The global aggregation and update occurred in line 5 to 6. Of course, this process needs sharing information among multiple nodes. In the right side, you can see several equations for parameter updates, include some expressions that are shown in previous slides. The problem formulation begins with this equation. This represents the global loss function, which is minimized subject to a given resource constraint for a learning task. To compute the last loss value at the k+1 step of global aggregation, there are terms with t+1 and k+1. R sub m denotes the total budget of type M resource. However, it's generally impossible to find an exact analytical expression to relate tau and k with the loss function, because it depends on the convergence property of gradient descent and the frequency of global aggregation. Moreover, the resource consumptions C sub m and B sub m can be time-varying. This slide represents the process of approximate solution. You can find specific proof for these theorems in section 5. Theorem 1 gives an upper bound of the difference between distributed and centralized gradient descents for each iteration interval k, assuming that v sub k of t in the centralized gradient descent is synchronized with w of t at the beginning of each interval k. The minimization of f of w super f in previous objective function is equivalent to minimizing f of w super f minus f of w star in theorem 2, because when a global loss function f of w is given, its minimum value f of w star is constant. And utilizing theorem 1 and 2, you can get a new objective function on the right bottom side through some substitution in the blue box. Let's look at some denotations. C sub m and B sub m are related to resource consumption, and these are referred in previous slides. And rho is Lipschitz parameter, beta is smoothness parameter, and delta is gradient divergence. These parameters are related to loss function characteristics. Then eta is gradient descent step size, and pi is set to the control parameter, since it's hard to know the value of pi. We need w star to find the value. Despite these processes, there is no closed form solution for tau star, because g of tau includes both polynomial and exponential terms of tau. But we can compute g of tau within a finite range of tau to tau star because tau star can only be a positive integer. Here is the algorithm for the aggregator. The input contains resource budget R, control parameter pi, search range parameter gamma, and tau max. The output is the final model parameters W super F. In line 11, the aggregation process begins by receiving estimated parameters from each node. In lines 17 to 19, it estimates global parameters for updating tau star in line 20. In here, search range parameter gamma limits the search space and avoids tau star growing too quickly. And the maximum value of tau max mitigates the possibility of system operating beyond the resource budget. In line 24, the aggregator monitors the total resource consumption of each resource type M. If it exceeds the budget, it stops learning and returns the final result. The computational complexity of this algorithm is shown on the right side. The algorithm computes local parameters collected from n nodes for m resource types. In addition, there is a linear search step in line 20, which has at most tau max steps. Here is the algorithm for edge node. This procedure begins by receiving a global model parameter and tau star value from the aggregator. For estimating some local parameters used for computing tau star at the aggregator, each node needs to have access to both its local model parameter, which is W sub I of t, and the global model parameter W of t, see line 6 to 7. The red boxes are only available from the second global aggregation step after initialization, since they need estimates obtained in previous global aggregation step. In line 8 to 12, performs the local update during tau star steps and transmits updated local model parameters with estimated consumption of M-types resource to the aggregator in line 13 to 15. The computational complexity of this algorithm is T plus Km, where T steps of local updates in total, and Km corresponds to the additional local processing for resource consumption at each node. From now on, we'll check the experimentation setup through a few slides. For the resource definition, they set M to 1, which means single resource type. Specifically, they considers time as the resource. Therefore, the value of C and B correspond to the actual time used for local update and global aggregation respectively. For the baselines, A is a centralized gradient descent, where the entire training dataset is stored on a single edge node, and the model is trained directly using a centralized gradient descent procedure. B is a canonical federated learning approach, which is equivalent to using a fixed value of tau. C is a synchronous distributed gradient descent, which is equivalent to fixing tau to 1. Also, they extend to SGD, which is stochastic gradient descent. This approach is efficient where the amount of training dataset is quite large. For models, the table 1 represents a summary of the loss functions of 4 models used in this experimentation. The loss functions for squared SVM and linear regression model are convex, whereas the loss functions for k-means and CNN are non-convex. And for datasets, 5 kinds of datasets are used in this experimentation. MNIST O is the original MNIST dataset. It contains grayscale images of handwritten digits. An energy dataset contains record of measurements from the energy consumptions of appliances and lights. User knowledge modeling dataset contains samples, each with 5 attributes, summarizing the user interaction with a web environment. MNIST F has the same format as MNIST O, but includes images of fashion items instead of digits. CIFAR 10 dataset includes color images of 10 different types of objects. There are 4 cases of data distribution. In case 1, each node has uniform but not full information. In case 2, each node has non-uniform information. In case 3, each node has the entire dataset, so each node has the same information. In case 4, the first half of the nodes, as in case 1, the other half of the nodes, as in case 2. This represents a combined uniform and non-uniform case. And you can see training and control parameters as well. Here is the result of the first set of experiments. In this experiment, the SVM, linear regression, and k-means models were trained on the prototype system. But due to the resource limitation of Raspberry Pi, the CNN model was trained in a simulated environment of 5 nodes. We can see the proposed approach only has one data point because the value of tau is adaptive. The marker location shows the average tau star with the corresponding loss or accuracy. The proposed approach performs close to the optimal point for all cases and all models. Of course, the empirically optimal value of tau is different for different cases and models. In some cases, the distributed approach can perform better than the centralized approach because for a given amount of time budget, federated learning is able to use all the resources at multiple nodes. For DGD approaches, case 3 does not perform as well as case 1 because the amount of data at each node in case 3 is larger than that in case 1. Due to the high complexity of evaluating CNN models and linear regression and k-means model do not provide accuracy values, experiments focus on the SVM model in following. Results of SVM SGD for the number of nodes are shown in the left figure, which are obtained in the simulated environment. We can see the proposed approach performs better than or similar to the fixed tau to 10 baseline in all cases. The value of tau is empirically a good value for non-adaptive tau according to the results in previous experiment. In the right side figure, the global aggregation time is scaled by the adjustment factor. One would intuitively expect a larger global aggregation time generally results in a larger tau star for the proposed algorithm. Comparing to the fixed tau to 10 baseline, the proposed algorithm performs better in all cases. The impact of the total time budget on the prototype system is shown in the left side figure. Except for case 3, where all nodes have the same dataset, the value of tau star of proposed algorithm decreases with the total time budget. This means tau star becomes close to 1 when the resource budget is large enough. Also, we can see the proposed algorithm performs better than or similar to the fixed tau to 10 baseline in all cases. On the right side, the sensitivity of the control parameter pi evaluated on the prototype system is shown. We can see the relationship among tau star in different cases is mostly maintained with different values of pi. The value of tau star decreases approximately linearly with log pi. For case 3, tau star remains the same with different pi because h of tau equals to 0. Moreover, g of tau and pi are inversely related but independently of tau in this case. This slide represents a result of synchronous versus asynchronous approach. Asynchronous gradient descent is able to fully utilize the available computational resource at each node by running more gradient descent steps at more faster nodes. However, this may hurt the overall performance. We can see that the performance of asynchronous gradient descent is much worse than synchronous gradient descent for non-uniform data distribution in case 2 and 4 with slower convergence, sudden changes, and convergence to higher loss and lower accuracy values. This is because the model tends to overfit the datasets on the faster nodes compared to the slower nodes. In case 1 and 3, with uniform data distribution, asynchronous gradient descent performs similar as or slightly better than synchronous gradient descent. Since the datasets at faster node and slower node are similar or equal. To wrap this up, this study has analyzed the convergence bound for federated learning with non-IID data, and it proposed a control algorithm concerns trade-off between local update and global aggregation to minimize the loss function under a resource budget constraint. Also, it confirms the effectiveness of this algorithm with extensive experimentation. At the end of the conclusion, we can find some future work items written here. Thank you for your attention.